Hello, welcome to my presentation. My topic is optimizing support locations in structural design. My name is Yiming Mike Xie. My co-authors are Ting-Uei Lee and Xianchuan Meng. We are from the Center for Innovative Structures and Materials of RMIT University, Melbourne, Australia. Nowadays, topology optimization techniques are widely used in many disciplines, including architecture design. Here is an example of an art museum designed by applying the bi-directional evolutionary structure optimization method using a Grasshopper plugin, Amoeba. Both the BESO technique and the Amoeba software have been developed by my team. Traditionally, structural optimization is performed by first prescribe the boundary conditions, so the support locations are fixed. In the current study, we want to find out the best support locations. This is important because support locations may influence both architectural appearance and structural performance. We have developed support optimization techniques for two classes of problems. In class 1, we use line-based supports and try to identify the optimal column locations under a flat roof. In class 2, we add one layer of elements to a continuum structure and try to find the best support locations. The support optimization is achieved by using the Optimality Criteria. For the column support optimization, we require the design variable to be proportional to the axial stress in each column. For the continuum structure, we require the density of the support element to be proportional to the square root of the strainage density. In fact, these two algorithms are equivalent because the square root of the strainage density would be proportional to the stress. I want to add that in the continuum structure, the topology of the main structure would be determined using the BESO method. Here is an example of finding the optimum column locations under a complex roof. The number of final columns is 7. In the initial design, there are over 1,000 possible column locations. In such a case, it is impossible to determine such a large number of combinations of possible column locations manually. But using our optimization method, we can find the best column locations, which gives the lowest compliance value or the highest stiffness value compared to the manually determined column locations. Here is an example of class 2 optimization problem for the supports. So this is a continuum shell, and we add one layer of support elements at the base. Using our support optimization algorithm, we can find a solution which has much lower compliance than all the other manually determined support locations. We can also perform the support optimization and the structure topology optimization simultaneously. As shown in these three examples, we are trying to determine the supports and also change the structure topology at the same time. The designer may prescribe the number of supports. Using our algorithm, the computer will perform the topology optimization for the main structure and also the location of the prescribed number of supports at the same time. Here is a 3D example of performing the support location optimization and the structure topology optimization simultaneously. The user may prescribe the number of supports, and the algorithm would automatically find the best locations for these supports and the corresponding optimal topologies. The conclusions from this study are: 1. Treating support locations as additional design variables provides new opportunities to significantly improve the structural performance. 2. The proposed method was developed based on an optimality criteria algorithm, which allows continuous variations of the design variables for the columns or the support elements. 3. The number of supports significantly affects the formation of the structural topology. 4. Optimizing the support locations may substantially increase the overall stiffness of the structure. Thank you very much for your attention. I would welcome any questions or suggestions.